Hi and welcome to my read and work through of Generating Functionology by Herbert Wolf, episode number 6. So last time I finished section 1.5 of the book and I was going to move on to 1.6 straight away, but when I watched through my last video I had a few things that I'd like to remark on. First thing I want to talk about is the formula that we had. We had the Bnx, which we had defined as sum of k greater than or equal to 0, n choose k, x to the k. And we proved in the book by induction on n that this is equal to 1 plus x to the n. Now it was sort of mentioned in the book that this is true for all n, which I don't really know if that's true. We've certainly not proved it to my knowledge, but it was also mentioned later on in the book that this is true for all n an integer. So, and we can prove that it works for all integers. We've proved that it works for all non-negative integers n, and it's also true, easy to show that it's true for all integers n. So I'm quickly going to discuss that here. And the way we got this for integers n was we had the following recurrence relation. So we had that n choose k was equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And the way we obtained this recurrence relation was by literally considering subset of size k of n objects and considering those which had a particular object and those which didn't have a particular fixed object of those subsets of size k. And that's how we got this. So we don't know that this is going to work for anything other than n a non-negative integer and k an integer between 0 and n. So first thing I want to do is prove that this holds for all n complex numbers. So true for all n complex. And we started with n choose k being, well, we were calling it, I think, f n k. We started with that being the number of ways to choose k objects from n objects. And what we did is using the generating functions, we derived the following formula that n choose k was equal to n times n minus 1 times n minus 2 n minus k plus 1 over k factorial. And then we use this definition here to define this for all n complex numbers. So we can take this formula here and plug it into this and see if this satisfies given any old n. So let's look at that. So that's fairly quick and easy to do. So let's look at, let n be any complex number. Let's look at n minus 1 choose k minus 1 plus n minus 1 choose k. So we'll have n minus 1 k minus 1 plus n minus 1 k, which is going to be equal to, it's going to be, well, n choose k, this, we're going to have n minus 1 n minus 2 dot dot dot, and it's going to be n minus k plus 1. So if you replace n with n minus 1 and k with k minus 1 in this, it's exactly the same thing. The minus 1s get cancelled out, and it's going to be over k plus 1 plus k minus 1 factorial, and this bit here is going to be plus n minus 1, n minus 2, dot dot dot. So this time it's going to be n minus 1 minus k plus 1. So it just goes all the way down to n minus k over k factorial. And noting that k factorial is just k minus 1 factorial times k, I'm going to multiply the top and the bottom of this fraction here by k. So what this will become is 1 over k factorial n minus 1, n minus 2, dot dot dot, n minus k plus 1 times k plus n minus 1 dot 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 to n minus k. This is equal to 1 over k factorial. Now both of these terms here have this as a factor, so this is equal to n minus 1, n minus 2, n minus k. Sorry, there's fireworks in the background. Recording this on bonfire now. This one is n minus 1 times n minus 2 to n minus k, and then times n minus k plus no. They've both got this bit as a factor. It goes to n minus k plus 1, and so this is k plus, and then it's n minus 1 times n minus 2, n minus k plus 1, and then n minus k, so it's plus n minus k. Equals, so 1 over k factorial, n minus 1 to n minus k plus 1. Then this here was just n, and I'm not going to write it here, I'm just going to write it on the left. And you can see precisely this is the definition of n choose k. So we have established that the recurrence relation n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k is valid for all n a complex number and k any non-negative integer. Cool. So using that, we can now easily show that the Bnx is equal to 1 plus x to the n for the negative integers n, because if we recall last time, we used that recurrence relation, this recurrence relation to prove that Bnx was equal to 1 plus x Bn minus 1x, for n greater than or equal to 1. But we used the recurrence relation to get this, and there's no reason because now the recurrence relation works for all n complex number. This holds for all n complex number. You just derive it in exactly the same way. All complex n. In particular, it works for n in integers. So if you let n equals 0, b0x, which was equal to 1, is equal to 1 plus x b 0 minus 1 minus 1x. So that means that b minus 1x equals 1 over 1 plus x. And continuing this, we have that if you let n equals minus 1 here, you'd have b minus 1x equals 1 plus x b minus 1 minus 1 minus 2 x. This implies that b minus 2x equals 1 over 1 plus x squared, and continuing like that, you would get that b minus nx is equal to 1 over 1 plus x to the n, a non-negative integer. And that follows by easy induction. So, yeah. But if you want to, if you're curious as to whether this holds for all n complex numbers, say, you have to start wondering, well, what is a power of a complex number? And it suddenly gets a little bit technical. I'm sure there's a way of treating this, and probably it's true, but in some sense that this is always true, but in no sense have we gotten to prove that yet. Don't know if that sort of thing will ever be covered in this book at all, to be honest. But if we just consider n a half, for example, which is square root, so 1 plus x to a half is square root of 1 plus x, and we already know that there are 2 square roots of everything. Every number has 2 square roots. Because if you've got you consider, well, what's the square root of z? Well, if y squared equals z, then y is the square root of z. Well, equally, minus y squared will then be z. So every complex number has 2 square roots. So just writing 1 plus x to the half isn't well defined. You'd need to say more, and you'd need to explain what is going on, and it would get quite technical. So that's all I wanted to say about that. But at least with the material we've already developed, we can very easily prove that this holds for negative integers as well. So that's cool. The next thing I wanted to address was the radius of convergence issue that was mentioned. It was mentioned in the book that Bnx, defined as this power series, n choose k, x to the k, has radius of convergence one, or converges if the absolute value of x is less than 1 for any n not a non-negative integer. So I wanted to prove that, and it's very easy to prove actually using the ratio test. So if n is a non-negative integer, we know that this is just 1 plus x to the n. Now obviously you have no trouble with this diverging for any value of x you choose, because it's just a polynomial, and you can always evaluate polynomial at anything. As in, there are only finitely many terms in this expansion. You don't get an infinite power series. However, as soon as n isn't a non-negative integer, this n choose k is non-zero for every k. So you do have a power series, and you can stop thinking about, oh, what was radius convergence? So it turns out to be 1. And so all we need to do is look at the ratio test, really. And so if I note that n choose k, which is n times n minus 1 dot 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 to n minus k plus 1 over k factorial, I'm going to rewrite this as in the following form. So product from I equals 0 to k minus 1 n minus I over I plus 1. This will give us this. This is n minus 0, n minus 1, and so on to n minus k minus 1. And the I plus 1 is just going from 1 to k, and you get 1 times 2 times 3 times 4, and so on, until you get k factorial on the bottom. So it's the same thing. And so in the ratio test, what we do is we look at the ratio between consecutive terms in the power series and see if a limit exists. So we consider lim k to infinity of n plus 1 choose k over n choose k. And this is lim, as k goes to infinity, of this product. So that we need to take absolute values here. So the top is going to be the product, I equals 0 to k. Let's see. Sorry. This is n k plus 1. As it's k that's being summed over. So, in this formula, we go from I equals 0 to k plus 1 minus 1, just k. And we get n minus I over I plus 1 divided by product from I equals 0 to k minus 1. Same thing, n minus I over I plus 1. And the first k factors of each product cancel. So, I mean, this is just the first k terms of this. So, all this is lim k to infinity of this for when I is k. So, n minus k over k plus 1. And to make this explicit and easy, this is lim as k goes to infinity. I'm going to rewrite this as n minus 1 minus, sorry, I'm going to write it as n plus 1 minus k plus 1 over k plus 1, which is equal to lim as k goes to infinity n plus 1 over k plus 1 minus k plus 1 over k plus 1, which is equal to lim as k goes to infinity n plus 1 over k plus 1 minus 1. And as k goes to infinity, n plus 1 stays the same, this term goes to 0. So we just get absolute value of minus 1, which is 1. So we have radius convergence, the reciprocal of 1, which is 1. So radius convergence is 1. And we couldn't, if we tried to do the same proof in the case when n was a non-negative integer, then we wouldn't be able to take this ratio because we'd be dividing by 0 for when k was large enough. So whenever n is a non-negative integer, obviously it converges everywhere, just a polynomial. When n is not a non-negative integer, we have radius convergence 1. It's easy to show. And one last thing I want to talk about, again about section 1.5, is when we were working out the sum. It was sum from n greater than or equal to 0 of n choose k, y to the n. We did this, and what we did is we looked at the fact that sum of n greater than or equal to 0, y to the n, b n x. This, we had calculated that this was 1 over 1 plus x y, and that this thing here was the x to the k coefficient of this thing, and so we were playing with this term here. And I really didn't understand the algebra. Oops. 1 plus x times y. I really didn't understand why they were doing what they were doing. But all they were doing is, so here this is like, think of this as a geometric series ratio 1 plus x times y. So this thing here is just, well, this thing here is just sum of n greater than or equal to 0 of y 1 plus x to the n. So it's a geometric series ratio of y times 1 plus x. And this is no good for finding what the coefficient of x to the k is, because the coefficient x to the k occurs in loads of different terms in this sum, and it's not very helpful. So what we do is we try and rearrange this fraction so that we have something of the form alpha over 1 minus beta x, where alpha and beta don't contain any x's, and then we'd just be able to write this would be equal to alpha times, so the sum of I equals 0 to infinity, beta to the n, beta to the I, x to the I, because it's a geometric series. So that's what we were doing here. And so it's very easy, once you realise that's what we're trying to do that now. So then this was equal to x to the coefficient of, so we're just trying to get this, so rewrite out the bottom fraction, 1 minus y minus x y. So we've got the 1 over something minus beta x, beta in this case would be y, but we don't have a 1 minus it, so what we did was divide the top and bottom here by 1 minus y, so it's just x to the coefficient of 1 over 1 minus y over 1, because there's 1 minus y bit here, divide that by 1 minus y, you get 1 minus y over 1 minus y x. So you can take that 1 over 1 minus y out, so it's got no x's in it, it's not going to affect it. 1 over 1 minus y over 1 minus y x, which is how we got that and then writing that as a geometric series, it's just y over 1 minus y x to the n. So the x to the k coefficient of this is just 1 over 1 minus y times y to the k over 1 minus y to the k. So that's how we ended up with y over 1 minus y k plus 1. So that was everything I wanted to address. I felt I didn't really address properly, or didn't address at all in my last video. Now we move on to section 1.6, another two variable case. This example will have a stronger combinatorial flavour than the preceding ones. It concerns the partitions of a set. By a partition of a set S, we will mean a collection of non-empty, pairwise disjoint sets whose union is S. Another name for a partition of S is an equivalence relation on S. The sets into which S is partitioned are called the classes of a partition. For instance, we can partition 5 in square brackets, asterisk, that's a footnote. Recall that square brackets n is the set of integers 1 to n. So 5 is the set 1, 2 to 5. One of them is 1, 2, 3, 4, 5. In this partition there are 3 classes, one of which contains 1, 2 and 3, another which contains only 4, while the other contains only 5. No significance attaches to the order of the elements within the classes, nor to the order of the classes. All that matters is who is together and who is apart. Here is a list of all of the partitions of 4 into 2 classes. There are exactly 7 partitions of 4 into 2 classes. The problem that we will address in this example is to discover how many partitions of n into k classes there are. Let nk denote this number. So it's sort of like n choose k, but they're using curly brackets. So I'm going to write this down. So nk equals partitions of n into k classes. So from what we've read, that means number of ways to split up the set 1, 2 to n into k subsets, each of which has at least one element in, and all of them are disjoint. It is called the Stirling number of the second kind, and our list above shows that 47 curly brackets is 42 curly brackets is 7. To find out more about these numbers, we will follow the method of generating functions. First, we will find a recurrence relation, then a few generating functions, then some exact formulas, etc. We begin with a recurrence formula for nk curly brackets, and the derivation will be quite similar to the one used in the previous example. Let positive integers n and k be given. Imagine that in front of you is a collection of all possible partitions of n into k classes. There are exactly nk of them. As in the binomial coefficient example, we will carve up this collection into two piles. Into the first pile go all of those partitions of square brackets n into k classes in which the letter n lives in a class all by itself. And into the second pile will go all other partitions, i.e. those in which the highest letter n lives in a class with other letters. So split this into two piles, pile 1, pile 2. So partitions where one class is just n by itself and all others. The question is, how many partitions are there in each of these two piles, expressed in terms of the Stirling numbers? Well, let's see if I can make any progress with this without reading ahead. So partitions where one class is just n, well, the first n minus 1 numbers all of the other partitions preceding this, all of the other classes in one of these partitions must be, the union of them all must be this set. So what we're going to have here is partitions of n minus 1 into k minus 1 classes. So this number here is going to be, I don't know what we call this, I'm going to say n minus 1, k minus 1. I'm just going to keep saying curly brackets, n minus 1, k minus 1 curly brackets. And all others, it seems like it might be a bit more tricky because, how do we do that? It's going to be this plus something, isn't it? I mean, n could be in a set of 2 elements, a set of 3 elements. I mean, if n was in a set of 2 elements, there would be n minus 1 choices of something to pair with n, so n minus 1, and then there would be k minus 2 remaining things to form the rest of the partition. So we've got n and n and another one, which cancels this n minus 1 factor, so there'll be n minus 2 left, and we need k minus 1 other classes, right? So it's going to be that. If n was in a class of 3 elements, there would be n minus 1 choose 2 other elements to pair with n, and then you've got n minus 3, k minus 1, because you'd have n minus 3 numbers left and you still need another k minus 1 partitions. So I think here we're going to have the sum so I think it's going to be the sum of n minus 1 choose k, oh no, not k, it's a different letter, I already used k, n minus 1 choose j times n minus 1 minus j k minus 1. Sum of j going from 1 to I don't know what, let's say n minus 1 for the time being, because this is these are all the possibilities where this will be non-zero, and so this works because when j is 1, you're just going to have n minus 1 here, and this is going to be n minus 2 k minus 1. And so if we wanted n to be partitioned with, let's say, n things, then you need to pick n minus 1 of them. So if n is going to be partitioned with n things, you need to pick another n minus 1 out of the remaining, sorry, if n is in the class of n has another n things, you need to pick those n things out of the remaining n minus 1 of them. So it's n minus 1 choose m. So this would correspond to j being n. So I'll just say j instead. So if n is with j things, there are n minus 1 choose j ways to get those other n things, and then you're going to want another k minus 1 partitions. And how many do you have left? N minus 1 plus j. So each term in this sum here corresponds to n being in a class with another j things. Okay, let's see if the book does this the same way. So, where were we? The question is, how many partitions are there in each of these two piles expressed in terms of the Stirling numbers? Consider the first pile. There, every partition has n living alone. Imagine marching through that pile and erasing the class n that appears in every single partition of the pile. If that were done, then what would remain after the erasures is exactly the complete collection of all partitions of n minus 1, the set n minus 1 square brackets, that is a set from 1 to n minus 1, into k minus 1 classes. There are n minus 1 k minus 1 curly brackets of these. So there must have been n minus 1 k minus 1 partitions in the first pile. And yeah, that's what I got there. So let's see what they say about pile 2. That was the easy one, but now consider the second pile. There, the letter n always lives in a class with other letters. Therefore, if we march through that pile and erase the letter n wherever it appears, we won't affect the number of classes. we'll still be looking at partitions with k classes. After erasing the letter n from everything, our pile now contains partitions of n-1 letters into k classes. However, each of these partitions appears not just once, but several times. For example, in the list 1.6.1, the second pile contains the partitions those ones. So what was 1.6.1? 1.6.1 was a list of all partitions of 4 into 2 classes. So we're looking at all of those, there's 7 of them, all of those which 4 lives with something else. And let's see, so here we have 6, and all of these have 4 with other elements, and the only one that didn't make it was the one where 4 is by itself. Okay. After we delete 4 from every one of them, we get this list. What we are looking at is the list of all partitions of 3 into 2 classes where each partition has been written down twice. Hence the list contains exactly 2, 3, 2 curly brackets partitions. Well, this isn't the way I looked at it, but are we going to get something similar? Perhaps not. Perhaps not. Perhaps we're going to get a different recurrence relation here. So where were we? Hence the list contains exactly 2, 3 curly brackets, 2 partitions. Well, why might that be? So if 4 lived with one other element, okay. So for every partition of 3, so for example, every partition of 3 into 2, so for example 1, 2, 3, we have to add the 4, we can add the 4 into one of them, and we can either have a 4 in here or the 4 in there. So this would come from both 1, 2, 4, 3, or 1, 2, 3, 4. And for every partition of 3, you can either add the 4 to the first one or add 4 to the second one. So yeah, you're going to get 2 partitions of 3 into 2. So in our case, we were after pile 2. So what would we get? Well, if we delete, as it said, if we delete 4, we're going to get partitions of n-1. Sorry, if we delete n, you're going to get partitions of n-1 into, still it's going to be k classes. However, 4, given a class, one of these, you could add 4 to any of the k of them. So it's just going to be k. Well, that's much nicer than what I've got. Well, I guess that gives us an identity already. Assuming what I did here was right. So this is equal to this sum here. Let's carry on. So in the general case, after erasing n from everything in the second pile, we will be looking at the list of all partitions of n-1 into k classes where every such partition will have been written down k times. Hence, the list will contain exactly k, curly brackets, n-1, k partitions. Therefore, the second pile must have also contained k, n-1 k partitions, before the erasure of m. The original list of n, k curly brackets partitions was therefore split into two piles, the first of which contained n-1, k-1 partitions, and the second of which contained k, n-1, k partitions. It must therefore be true that nk equals n-1, k-1 plus k, n-1, k. So I'm going to write that down. That's our first, and that's pretty decent. That's pretty similar. So nk curly brackets equals n-1, k-1 plus k, n-1, k. Then this is going to be presumably for all n integer greater than or equal to 0, and I guess you could also have k greater than or equal to 0, any integer. As soon as k exceeds n, it's going to be 0. It's probably it's all going to make sense. And they've written nk equals question mark, question mark, question mark, question mark. I'm not sure what that is about. It's what? I don't know. Let's keep reading. To determine the range of n and k, let's extend the definition of nk to all pairs of integers. We put nk equals 0 if k is greater than n. So, yeah. Or n less than 0 or k less than 0. Further, n0, so splitting n into 0 partitions equals 0 if n is not equal to 0, and we will take 0, 0 to be 1. With those conventions, the recurrence above is valid for all nk other than 0, 0. And we have that the recurrence relation holds for all nk non-zero, not both 0, and 0, 0 equals 1. I just took a little break to think about this a little bit, because I thought it was a bit strange how they've defined these values for all the negative things, and they have an exception in the recurrence relations for when both n and k are 0. So I was wondering why they did that. I was wondering if there is a forced solution, if once we know positive n's and k's, once we know the values for positive n and k, if it forces all of the negative values as well. So I was just thinking about that a little bit. And so the best way of describing this perhaps is drawing a picture. So if I draw a grid, these are all meant to be squares, and if we imagine that each square represents a point on the integer lattice, so let's call this 0, 0, I'm going to have n's going in this direction, k's going in this direction, so this will be 1, 0, 2, 0, 3, 0. So these are that are stirling numbers in these boxes, and our occurrence relation was nk. So say this was nk equals n-1, k-1. That would, if that was nk, that would correspond to this one. So subtracting one of the n's and subtracting one of the k's, plus k n-1 k. So that would be this one here. So we have this triangular shape, And everything inside this triangular shape, they're all they all satisfy a linear equation. So once you know two of them, you know the third, provided that k is non-zero, of course. If k was 0, which would correspond to this column here, no, sorry, it corresponds to this row here. If k was 0, then this term vanishes, and we just end up with nk is equal to n minus 1 k minus 1. So this would be nk. If this was nk, then this is n minus 1 k minus 1. So this is equal to this, whatever this one is. So this one would be 0. No, it would be 1 minus 1. Yep, and this would be 0 minus 1. And this would be 0. No, minus 1 minus 1. And it would be equal to that, and so on. So if we didn't have the exception, we would have that 0, 0 is equal to minus 1, minus 1. And it seems that the author doesn't want that, so he has an exception for this case. But otherwise, apart from this exception of when k is 0, we always have things in this sort of kind of L shape, gamma shape, maybe you could call it. You know, if you know two of them, you know the third. They all satisfy a linear equation together. So what we know for sure, so if I rewrite my grid, n's go this way, k's go this way, and say this is 1, 1 here. We know we can work out the Stirling numbers for this region up here, like based on what we know already. This would be when k is 1, so these are all going to be 1, and this is when n is 1, so these values in here will all be 0, and these will all be 1s, and then we can use the recurrence relation, which I'm representing by this shape here, to work out all of the rest. So once you know this and this, you know this one here, so it is this plus 1 plus 0 in this case, and then this is 1 plus 1 times 1, 1 plus 2, 1 plus 1 times 2, I think. Does that make sense? So that's 1, 1, that's... no, this would be k equals to 2, so it's 1 plus 2 times 2, that should be a 3, 1 plus 2 times 3, this should be a 7, so yeah, this corresponds to 4, 2. And then to calculate this row, it's this plus 3 times that, this plus 3 times that, this plus 3 times that, and so on. And we can calculate this whole upper right hand corner of the integer plane. For this column here, this row here, sorry, when k is 0, if we apply the recurrence relation, we would have that. No, this is a k equals 1 row. No, this is a k equals 0 row, but yes, this is k equals, so k equals 0, k equals 1, k equals 2. But if we wanted to calculate this, we would apply it, say, to this, and this is equal to this plus this. So we can, this plus this must equal this, so you get to 0 there, and these all end up being zeros, and so on. So we know these are all zeros. And then if we were to apply the recurrence relation for when k is 0, this would have to be equal to this, and this would have to be equal to this, and so on. However, for the 0, 0 position, what we want is that this is 1 as opposed to 0. And if we set this as 1, as I mentioned before, we end up with minus 1 having to be 1, which the author clearly doesn't want. But anyway, so we can now work out this, because this plus this has to be equal to that, so this has to be 0, and this plus twice that must be equal to that, and so you get all these 0 up here. And if, for example, suppose we didn't keep the exception, we kept it as 1 in this minus 1 position, then this plus this would have to be, let's see, so this is equal to, so what would go in this position, we don't know, it could be anything. But we can calculate, we can continue to calculate down here. So it'd be this minus this would have to be equal to 0. So we could calculate everything down here. So we would have this whole region of the integer lattice, which we would be able to calculate from the values we already know from just looking at the combinatorics of the situation. Though with this here, this is different than what the author wants in the minus 1 position. And then what goes on in this section is not forced at all, because from this point, every time we try and work out another value in this section, we need to insert this shape somehow and know 2 of them. So if we were to plug this in here, well, we only know 1 of them, that's not enough to tell us. So we could put any values you wanted, for example, on this row all the way along here for k equals 0 row. And then we could calculate them upwards and downwards, and we could calculate the whole plane. So these could be chosen completely arbitrarily, and it would force the rest of them, and we would have an array of integers, well, an integer array of values which satisfy the recurrence relations, but we're just stuck in junk. So what the author's done is ignored the recurrence relation for when both n and k are 0, which corresponds to this block here. They set this to be 0, and then is essentially just set this row to be all 0s, and then it forces all these to be 0s and all these to be 0s down here, everything else to be 0. And recurrence relation is going to hold, except for the one exception that we set. So I just thought I would check that the recurrence relations do hold when he sets them to be the values that he has set. And I wondered if that was the only possible solution. So it's not. So I think it's quite a strange choice that is decided to. It's quite strange that it's decided to force it like this, to set everything else, everything we're not interested in, to 0, and then we have an exception in the recurrence relation at a specific point. I feel like it's a bit strange. I suspect that we won't really need this, and perhaps it's. We'll be able to do the calculation just fine, looking at k and n greater than or equal to 1. Maybe he just doesn't want to be careful with his indices when taking summations and stuff. So let's see what happens. So the stage is now set for finding the generating functions. Again, there are 3 natural candidates for generating functions that might be findable, namely ANY is the sum over k of nk curly brackets, y to the k. bkx is equal to the sum over n of nk curly brackets, x to the n, and cxy, which is the sum over all of n and all of k, n choose k, n curly brackets, k, x to the n, y to the k. Before we plunge into the calculations, let's pause for a moment to develop some intuition about which of these choices is likely to succeed. To find ANY will involve multiplying 1.6.3 by y to the k and summing over k. Do you see any problems with that? Well, there are some, and they arise from the factor of k in the second term on the right. Indeed, after multiplying by y to the k and summing over k, we will have to deal with something like sum over k, and curly brackets k, y to the k. This is certainly possible to think about, since it is related to the derivative of a and y, but we do have a complication here. If instead we choose to find bkx, we multiply 1.6.3 by x to the n and sum on n. Then the factor of k that seemed to be troublesome is not involved in the sum, and we can take that k outside of the sum as a multiplicative factor. Comparing these, let's vote for the latter approach and try to find the functions bkx for k greater than or equal to 0. Hence, multiply 1.6.3 by x to the n and sum over n. And we get the following. So let's just do that. So you're going to have, so b k x is equal to the sum over n, nk in curly brackets, x to the n, and our occurrence relation is nk equals n minus 1 k minus 1 plus k n minus 1 k. So we're going to multiply both sides by x to the n and sum over all n. So we'll get, this is going to be bk on the left, bkx equals sum of n x to the n n minus 1 k minus 1 plus k sum of over n x to the n n minus 1 k. So what do we have here? This, well, we have a offset of an n, so yeah, I guess the way they defined all these for all of the other integers was just so that we can do shifts around like this. So if I add n 1 to both of these n's, we would get x the n plus 1 n k minus 1 here, sum over n. We'll do the same here, x to the n plus 1 n k. Yep, and so though we would have to be careful. We'd need to make sure that k was non-zero. So if k was greater than or equal to 1, did they say that in the book? No, it says k greater than or equal to 0. So, well, this equation won't be true for when k is 0, right? Or maybe it will be. Oh well, whatever, I'll think about that later. Let's continue anyway. So this is just going to be equal to x b k minus 1 x plus k x b k x. Is that what they have? Yeah. And they've written k greater than or equal to 1 here, and that b0x is equal to 1. So what would b0x be? So b0x is the sum, so over n, n0, x to the n, and this is only non-zero if n is 0, so yep, that's just 1. Okay. then they solved this for bk in terms of big K minus 1. So we had bkx equals x bk minus 1 x plus kx bkx. Therefore bkx 1 minus kx equals x bk minus 1x, and bkx equals x over 1 minus kx bk minus 1x. And finally, this leads to the evaluation. Bkx is equal to, so well, it's just going to be the product, so product of all of these over the k's, for k going from 1 to whatever your, so if k was instead, yeah, so sorry, I'll just write this out. So it's going to be bx, it's going to be equal to the product from I equals 1 to k, x over 1 minus ix times b 0x, which was 1, times 1. So I'll just leave it out. So this is x to the k over product from I equals 1 to k, 1 minus ix. And this holds for all k greater than or equal to 0. The problem of finding an explicit formula for Stirling numbers could therefore be solved if we could find the power series expansion of the function that appears in 1.6.5. That, in turn, calls for a dose of partial fractions, not of Taylor's formula. The partial fraction expansion in question here has the form, oh goodness, this is going to get pretty crazy, I feel. So you're going to be able to express it as a sum of linear combinations of a 1 over 1 minus jx. To find all of the alphas, we fix r for r between 1 and k, multiply both sides by 1 minus rx, and let x equal 1 over r. I'm getting some mad formulas. It's looking very complicated here, but it looks very fun. Okay, I'm just going to work through this, and then I'll probably stop this episode and continue on another time. So let's work through this. So if we're going to look at 1 over the product from I equal 1 to k of 1 minus ix, it's saying that this is going to be equal to the sum from I equals 1 to k alpha I over 1 minus ix, and we want to find the alpha i's. I notice here they have a 1 on top of their partial fraction. They're not using an x to the k, which is the form of the thing we're actually after. But anyway, so we take some r, take some r between 1 and k, and we're trying to find alpha r. And the trick is to multiply both sides by 1 minus rx. And so this on the left is going to become 1 over the sum product, so I between 1 and k, but I is not equal to r. Oops, we missed that one out of product. Equals sum from I equals 1 to k, alpha I 1 minus ix, oops, sorry, 1 minus rx over 1 minus ix. Now if we look at this sum, and I just, firstly I take out the I equals r term, just like I did in this product. So first I between k, but I is not equal to r, of alpha I 1 minus rx over 1 minus ix. So we've got this part, and then we've also got the alpha, so plus alpha r 1 minus rx over 1 minus rx, but that's just 1, so I'm going to get rid of that. So we're going to have this whole thing. So what we're going to do is we're going to let x be equal to, was it 1 over r? Yes, it was 1 over r, which is going to make this bit 0, and it gives us a formula for alpha r. So alpha r equals 1 over product of 1 between I between 1 and k and I not equal to r of 1 minus I over r. Alright, and so where did they get? Did they get to that point? So they have alpha r is equal to, yep, 1 over 1 minus 1 over r times 1 minus 2 over r times dot 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 1 minus r minus 1 over r, and then we miss out 1 minus r over r, and then we have the rest of them. There you go, that's exactly what we've got there. And then they multiply the top and the bottom by r to the k minus 1. So, because there's k minus 1 products here, so r to the k minus 1 over product. So 1 is less than equal to I, less than equal to k. I is not equal to r. So we've multiplied each one by r, so it's going to be r minus I. So they're going to then split this product here into 2. So what's going on here, so we had this formula here, what we've got now is that for when I is less than r, this is positive, so I'm going to split it into 2. So we got alpha r is equal to r to the k minus 1 over product. So I'm going to split it into the products for I being between 1 and r, so I is between 1 and r but less than r, only greater than or equal to 1, r minus I times, and the other part, so I is bigger than r minus I. Now this thing here, these terms are all going to be negative, and so this value here is going to, well, yeah, so I'm going to make them all positive by taking out all of the minus 1. So how many factors are in this product? K minus r factors. So this is going to be, so this will be equal to r to the k minus 1 over, so 1 less than equal to I less than r minus I times, so minus 1 to the k minus r, and then s and I less than or equal to k, I minus r. So now everything in the products are positive. So this value here, as I goes from 1 to r minus 1, this is going to go from r minus 1 to 1. So this is just r minus 1 times r minus 2 times r minus 3 all the way down to 1. It's r minus 1 factorial. And this bit here, as I goes from r plus 1 to k, when I is r plus 1, this is just 1, and when I is k, this is k minus r. So it's going to be k minus r factorial. So therefore we get, I hope this is the same as what they've got, minus 1 to the k minus r. We can just take this minus up to here, because minus 1 is the inverse, multiplicative inverse of itself, r to the k minus 1 over r minus 1 factorial k minus r factorial. Is that what they've got? They've got minus 1 to k minus r is equal to r to the k minus 1 over r minus 1 factorial times r minus k minus r factorial. Cool. And so they then go on to try and find an explicit formula for nk in curly brackets. So yeah, indeed. So we have, so what did we have? Let's try and remember where we were. So we had b, it was bkx was equal to the sum over n of nk in curly brackets x to the n. So if we want to know nk, what we need is the x to the k. No, we need x to the nth coefficient. So nk is equal to the x to the nth coefficient of bkx. And what did we have? We had that we knew that what bkx was. It was x to the k over the product of I between 1 and k, 1 minus I x. So we need the x to the nth coefficient of this. And what is this? Well, we've got this x to the k up here. So the x to the nth coefficient of this thing is it going to be, so if I want to take this x to the k, this k, and put it in here, do I add it or subtract it to the end? Let's think. So if I divide this by x to the k, then what was once the x to the nth coefficient has become the x to the n minus kth coefficient. So this is equal to, so x to the n minus k coefficient of 1 over product between I, k, 1 minus ix. And we know that this is the x to the n minus kth coefficient of the partial fraction expansion. So this goes from I equals 1 to k, and it was alpha I over 1 minus ix. So, and we know all about this sort of thing. The x to the So the, let's say, j'th coefficient of, so x to the j of 1 over 1 minus ix. Well, this thing here is geometric series with ratio ix. So it's just going to be I to the j, I should imagine. So going from this is going to be equal to sum from I equals 1 to k alpha I times I to the n minus k. And we knew what the alpha i's were. We had a formula for those. So what are we going to get here? We're going to get that assuming I've not made any mistakes, I've not been following the book on this, I've just been doing it myself. So we're going to get that this is equal to the sum of I equals 1 to k of, and if you recall what alpha I was, it would be, well, I'm going to sum over r because we worked out what alpha r was. We'll have minus 1 to the k minus r, and I've got this, I'm going to also have r k minus 1, and I've got this factor here, I to the n minus k. Well, I replaced I with r, so it's going to be times r to the n minus k all over r minus 1 factorial k minus r factorial, and this times this is just going to be r to the n minus 1. So what we should get here is nk equals sum from r equals 1 to k minus 1 to the k minus r to the n minus 1. So the r to the n minus 1 could come outside here. R minus 1 factorial k minus r factorial. So let's see, what do they get? They have, they multiply the top and the bottom by another r, it seems, to get r to the n on top and an r factorial on the bottom. So if we multiply the top and bottom by an r, this becomes r to the n and this becomes r factorial. And now that appears to be the same as what they have. Yeah, it does. Okay. So, and that's just what we wanted, an explicit formula for nk in curly brackets. Do check that this formula yields that 4 and 2 in curly brackets is 7, which we already knew. At the same time, note that the formula says that n and 2 in curly brackets is 2 to the n minus I minus 1 for n greater than 0. Can you give an independent proof of that fact? So I'm just going to check that this works for 4 and 2. So 4, 2. So k is 2. We're going to have r summing from 1 to 2. I'm going to take this r to the n out. No, I can't take the r to the n out. R's being summed over. Never mind. I think I said that you could take the r out. It's not right. That's not right. So what do we have? So you're going to have minus 1 to the
k minus r, well, k is 2, so 2 minus r, r to the n was 4, r to the 4, divided by r factorial, and k is 2, so 2 minus r factorial. So this is just the sum of two individual things. So when r is 1, this is minus 1, 2, 1, 1 times 1 to the 4 over 1 factorial times 2 minus 1 factorial plus the case when r is 2. So minus 1 to the 0 times 2 to the 4 divided by 2 factorial times 0 factorial. So this is minus 1 over 1 plus 2 to the 4, 16 over 2. So minus 1 plus 8 equals 7. It works. Well, that's a pretty crazy formula. Okay, so that's gone on pretty long, so I'm going to leave it there. It's the end of this episode. We're going to continue with this section 1.6 next episode. And this is pretty fun, isn't it? I like this. I'm going to have a little think about, check if anything that we did earlier with these BKXs when we were summing over the recurrence relation was ever affected by the exception that they have in the recurrence relation for when n and k is 0. Possibly doesn't. Yeah, so I just want to have a little think about that because I kind of ploughed ahead here just to see where it was going. So yeah, I'll do that next time. So thank you for watching and goodbye.